Number 7 is sort of like a companion to 1. This is pretty similar to the bullet dropped and fired example that I did at the end of class last time. So this bullet is fired with a speed of 800 meters per second. Let me see what the height is. 1 meter. Fired from 1 meter above the ground, 800 meters per second, and the angle is 3 degrees above horizontal. Okay. And we want to find out how long does it take for the bullet to hit the ground? How far away horizontally does it hit? So first of all, so it's going to look something like this. It's going to start out 1 meter above the ground, and it's going to take off. I mean, that's way more than 3 degrees, but it's going to take off at some angle above horizontal. And then it's going to follow a parabolic path like that. Whereas the bullet in number 6 started out like this, and then from there followed a parabolic path. So something like that. So that's what we're comparing, those two flights. Okay, I am going to choose my coordinate system origin to be on the ground right beneath where the bullet was launched, fired. And I'm going to choose my y-axis up. My time equals 0 is going to be the instant that it's fired. And time final is going to be, for A and B both, we're talking about stuff when it hits the ground. So time final has to be the instant, I guess, right before it hits the ground. And now we can figure out what we know and want. For part A, we're trying to figure out time final, so that's the thing we're looking for. The acceleration, we're assuming that there's no significant air resistance, so this is 0 for x, negative 9.81 for y. Pi, so it starts out at a height of 1 meter, and so pi is equal to 0, 1. PF, do we know anything about PF? Well, we know that it's going to be on the ground, so PFY is equal to 0. We're going to try to find PFX for part B. The initial velocity now, this is where very commonly you have to use a speed and an angle to calculate this, and that's what we're going to have to do here. So this is going to be 800 times the cosine of 3 degrees, and then 800 times the sine of 3 degrees. And that is, for the x component, 798.90, and for the y component, 41.87. Okay, so 798.90 and then 41.87. And then we don't know anything about V final, so I'll just leave that off. So the equation that we can use to find time final. Okay, so with this one, the video that I showed that, and one of the calculations we did showed that if you drop a bullet from a meter high and fire a bullet horizontally from a meter high, they're both going to take the same amount of time to hit the ground, and that time was 0.4515 seconds. Okay, that's what we figured out last time. So that's what we're comparing this to, is 0.4515 seconds. Okay, so let's just keep that in mind as we do this. So when I did the calculation where the gun was tilted up 0.1 degrees above horizontal, we got a time of like 0.64 seconds, which is a pretty surprising increase in the amount of time for how little that angle is. This is tilted up 3 degrees, which is still a really small angle, but it's a ton bigger than 0.1 degrees. So we expect this to be pretty significantly more than 0.4515. The time that we're going to see is probably still like surprising, even being ready for that, you know. So the equation that I think works is PFY is equal to PIY plus VIYTF plus 1/2 AY TF squared. And so 0 is equal to 1 plus 41.87 TF minus 4.905 TF squared. So since we have a quadratic term, a linear term, and a constant term, the quadratic formula is the best way to go. So here's our A, here's our B, here's our C. Negative 0.024 seconds. We don't want that one because it's negative and this is time. And the second one is 8.56 seconds, and that's the one we want. Okay, so by tilting the muzzle of the gun up 3 degrees, we went from a time of 0.4515 seconds to 8.56. So that's, getting close to 20 times as long to hit the ground. The reason it takes so long is, so what would be an equivalent, so when the bullet is fired horizontally, the equivalent one-dimensional amount of time is if you just take that bullet and drop it from rest, okay? So is there like an equivalent one-dimensional motion that you could compare to this? You know? And there is. And the answer is it's starting with something 1 meter off the ground and launching it straight up into the air with a speed equal to the y component of the velocity. And look how fast that is. That's like 90 miles an hour. And the reason that that's so big is that even though this is only tipped up 3 degrees, which is this tiny amount, if something's moving 800 miles an hour, even a small fraction of that 800 meters per second gets pretty big, you know? And that's what that y component gives you. Okay, so that's kind of how it works intuitively. And then let's figure out how far away it hits the ground. You can see from this picture, and you kind of have a sense, like if you're trying to throw a ball as far as you can, you don't throw it horizontally, you throw it up a little bit, and it's the same effect with a bullet. If you don't have any air resistance, which we don't in our calculation, then the farthest it's going to go is if you launch it at a 45 degree angle. That's something you could calculate. It's just kind of like something worth keeping in mind, I suppose. And so anything closer to 45 degrees makes it go farther. And so that's what this is going to do. So for part B now, we want to figure out what PFX is. And we can use this equation. PFX is equal to PIX plus VIXTF plus 1/2 AX TF squared. AX is equal to 0, so this one goes away. And we get that, so PFX, what we're trying to find, is equal to 0 plus 798.90 times 8.56 and you get 6838.58, which is a little over 5 miles. No, a little over 3 miles, 4 miles, something like that. A long way away. If it was just launched horizontally from a height of a meter, what you would get is 800 times the amount of time before it hits the ground. So it would only be 361.2 meters. So that's a pretty significant difference. Any questions about that one? Any questions about the basketball one? That was probably the hardest one I assigned you, I think. Anyone do that one yet? I think these are just due tonight, right? Mm-hmm. So the basketball one is funny because usually we're trying to calculate final positions and stuff. In that one, we're trying to calculate initial positions. But I don't know. If you have questions about it on Wednesday, I can go through it. Any other homework questions you want to see before I go on to some other examples? All right. Okay, so let's say, so this is like a party trick you can try later today. So here's you on a skateboard.
You're a good guard.
Thank you.
Real.
That's my real calling.
After this class and chemistry, I feel like I should have paid more attention in art class.
Yeah, right. Okay, so this is you, and let's say that you know that you can move on your skateboard at a speed of 5 meters per second. And you have like a little cup set on the floor over here. And it has a height of 0.15 meters. And you're going to drop this ball. And that ball is going to that path, it's important to remember that that path is always going to be part of some kind of parabola. And you want to drop that ball and make it land right in the cup. Okay, so the question is, how far away from the cup do you have to be when you drop that ball? And we'll say that you drop it from a height of 1 meter. 1 meter is just such a nice, simple number. Okay, so once you figure this out, you can put some tape on the floor, you can skateboard across, let go of the ball when you hit the tape, and it'll go in the cup, and you can win money off your stupid friends. This is not 1 meter. I was saying something as I was thinking about something else. This is what we're trying to find. So how far away do you have to be? How far away do you need to be at the drop for the ball to land in the cup? Okay, well, the first thing we have to do is choose a time equals 0, a time final, and a coordinate system location. I'm going to do what I always do and put my coordinate system on the ground beneath where it is at the start of the motion. And my time equals 0 is going to be the instant it's dropped. And the time final is going to be the instant that it reaches a height of 0.15 meters. Okay, so now do we know how long it's going to take? No, but we don't need that. I mean, we're not looking for that, so I'll leave it off for now. We do know the acceleration is going to be 0, negative 9.81. The initial position is, so in this coordinate system, at the instant it's dropped, the coordinates are 0 for x, 1 for y. P final, we know the y component is going to be 0.15 meters. And we're trying to figure out PFX. Then the initial velocity. Okay, so how do we know the initial velocity? Well, the velocity when something is dropped, at the instant it's dropped, is the velocity of what it's dropped from. This skateboard is moving horizontally at 5 meters per second. So if this is your coordinate system, the skateboard's velocity is like this. The length of that vector is 5, so this is 5, 0. And then we don't know the final velocity. Okay, so now if we're trying to find p of x, we know that has to come from an x equation. So you can check the 3 x equations. None of them would work in this case. And so no equation works. And so we're going to start instead by finding TF. Okay? And the nice thing about TF, the reason it's so useful is because it's the only variable that crosses over between the x equations and the y equations. And so you can try all 3 of the y equations. The one that works here is P F y is equal to PIY plus VIY TF plus 1/2 AY TF squared. So 0.15 is equal to 1 plus 0 minus 4.905 TF squared. And so I'm going to rewrite this as 0. Oh, no, I'm not. I'm going to rewrite this as negative 0.85 is equal to negative 4.905 TF squared. Divide both sides by negative 4.905. And you get that TF squared is equal to 0.173. And now take the square root of that. And TF is equal to plus or minus 0.416 seconds. And this is time, so we want the positive. So now that we have that TF, we have one more thing we can use to try to find PFX. And now we can use the equation PFX is equal to PIX plus VIX TF plus 1/2 AX TF squared. Remember that AX is equal to 0, so this goes away. And so PFX is equal to 0 plus 5 times 0.416 So PFX is equal to 2.08 meters. So if you put tape on the floor exactly 2.08 meters, 208 centimeters away from the cup, and you're going exactly that speed, you drop it exactly at that height, it'll land right in that cup. Any questions about that? Okay, let's do one more kind of similar one. Let's say that there's a helicopter and it is moving up, well, at an angle. And let's say this angle is 30 degrees. And let's say that this helicopter is moving. How fast can a helicopter go? Pretty fast, right? Maybe not when it's going that steep, though. Let's say 20 meters per second. And let's say that an object is dropped from the helicopter at a height of 25 meters. What's the height of the object at the highest point, at its highest point? And second, what's the velocity of the object? So what's the velocity vector of the object just before it hits the ground? Okay, so the first question here is, does it make sense to everybody that, like, does part A even make sense? We're talking about dropping this thing from a height of 25 meters. If you just drop this thing out the window, isn't it just going to go straight down from there? Right, the answer is, it has the same effect as this thing being launched with the velocity of the helicopter, okay? And so this object is going to, it starts here, but it's actually going to follow a parabolic path like that. And it's going to go up some amount at least before it starts coming back down. Okay, so for part A, I'm going to choose the ground, the coordinate system origin to be on the ground right beneath where it's dropped from, which is what I always do. And my time equals 0 is going to be the instant that it's dropped. And the time final is going to be the instant that it reaches the highest point. So as soon as you see something about highest point, what's the thing right away that you know you're going to use? What's the fact you know you're going to use?
Acceleration is 0.
Velocity, the y component of velocity is 0 at the highest point. So the instant it reaches the highest point. So let's list what we know and what we want. We don't know how long it's going to take. We do know the acceleration is 0, negative 9.81. The initial position is 0, 25. The initial velocity we can get from the speed and the angle of the helicopter. So if this is the coordinate system, we'll put the tail of the velocity vector at the origin. It has a magnitude of 20, and this angle is 30 degrees. So this will be 20 times the cosine of 30 degrees, 20 times the sine of 30 degrees. And that is 17.32 for x and 10 for y. I skipped what I usually do as the next one, PF. So what do we know about PF? We don't know anything, but we do want to find PFY. We're trying to find the height at time final. And then the last thing is, we've been waiting for this through the whole list. we know that PFY is equal to 0.
So we want PFY or PFX? Oh, VFY you said.
Yeah,
Okay,
I said
alright,
PF. Okay,
okay.
VFY we know
My
is 0.
bad. I think I heard.
I think I might have said that.
It's okay.
Okay, so, yes. Higher. Sure. All right, so is there an equation that works for these? I think the one that should work is 2ay times the quantity PFY minus PIY is equal to VFY squared minus VIY squared. So if you plug all this stuff in, you get negative 19.62 times the quantity PFY minus 25 is equal to VFY squared is 0 squared minus VIY squared, that's 10 squared. And remember that we're just squaring the 10, we're not squaring that negative. So now we can divide, so the right side ends up being negative 100. And then negative 100 divided by negative 19.62 says PFY minus 25 is equal to 5.10 meters. And therefore PFY is equal to 30.10 meters. So the speed of the helicopter makes this thing travel 5 meters up before it goes back down. Yeah.
So as the helicopter's going up?
Yeah, the helicopter keeps going. You're right about that. So the helicopter is just going to keep moving along a line like this.
Got it.
And the ball is going to, yeah.
Thank you.
Mm-hmm. Okay, so part B, now we want to figure out what's the velocity vector just before it hits the ground. So you always have to think about this when you go to part B's and part C's of problems. Is there any reason we need to choose a new time equals 0 or a time final? And yes, there is in this case. We can keep the same time equals 0, but the time final we have to change, okay? Because now we're trying to figure out something later than the time final we chose before. So our time equals 0 is still going to be the same. But our time final is going to be the instant just before it hits the ground. Okay, so what that means is, since our time equals 0 is the same as it was before, all the initial stuff we knew before is still true, but the final stuff is different. So we can't use our old position final, velocity final, any of that. Okay, we don't know how long it's going to take. We know that the acceleration is 0, negative 9.81. The initial position is the same as it was, that's 0.25. The final position, we know that the y component is equal to 0 because it's going to be on the ground. We don't know what the x final position is. Our initial velocity is the same as it was before. So that's 17.3210. And then this time we don't know anything about the final velocity. We are trying to figure out both of those two, we're trying to figure out V final, both components. All right, so is there any equation that lets us calculate either one of these components right away? I think we can calculate V final y using this equation. 2ay times the quantity pfy minus piy is equal to vfy squared minus viy squared. So negative 19.62 times the quantity 0 minus 25 is equal to vfy squared minus 10 squared. And so, let's see, that is going to be 492, 49.05, 25, 490.5, I think, is equal to VFY squared minus 100. And so VFY squared is equal to 590.5. Take the square root of both sides. And since we're taking a square root of a variable, we can have the positive or negative answer of 24.30 meters per second. Okay, if you do this and you're trying to solve for a time, then the decision is easy. We want the positive. But this time, notice, we're not trying to find a time. We're trying to find a velocity. And so you have to think physically about what's happening. Basically, right before this thing hits the ground, is it moving up or down? Down. Down is our negative. So in this case, we want negative. Okay, what about the x component? Well, there's two ways you could solve for the x component. The first way is, it turns out if you look for an equation, nothing works. So you can calculate TF and then calculate the x component of the velocity, and that'll work perfectly fine.
So once for the velocity is negative?
The y component is negative, yep, because it's on the way down, and down is negative. So the other thing, remember I mentioned this before, that in equations, you don't want to act like you don't want to write down that you know the x component of velocity at the end. But really you do, because the x component of the acceleration is 0, which means the x component of velocity doesn't change. So VFX is just going to be what it was at the start, which is 17.32 meters per second. That's because the x component of the velocity is constant. Yeah, right. So in any like free fall or projectile motion problem, the x component of the velocity stays the same. Okay. And so all this together says VF as a vector is equal to 17.32 negative 24.30. So if you wanted to draw that, if you wanted to, visualize the angle that this is moving at when it hits the ground, you could plot the point positive 17, negative 24, then make that the head of your vector and put the tail at the origin. And it's something like that. Any questions about that? Okay. Now, the last thing I want to do today is talk about something like this is basically what the lab this week is going to be about. This is an intuitive understanding of acceleration in 2D. Okay, so in 1D, acceleration only means that the speed is changing. And so if an object is speeding up, then the velocity and acceleration are in the same direction. And if an object is slowing down, then the velocity and acceleration are in opposite directions. Okay, so for example, if you have a ball rolling down a ramp, let's say the ball is rolling up the ramp actually at this instant. The incline of the ramp is going to make the ball slow down. And so the velocity of the ball is going to be this way, up the ramp. Since it's slowing down, the acceleration has to be opposite, so the acceleration is this way. I'll leave the vectors off, but. Okay, so we've done a lot of that kind of stuff. In 2 dimensions, though, it gets a little more complicated. In 2D, acceleration can do 2 things. It can cause a speed change. And or it can also make the object turn.
Do you always know whether it's speeding up or turning, like in the problem, or does that not matter?
I'm trying to think. most of the time, at least at first, yeah, like I just tell you that stuff and you have to use that. There are some other clues that can be given that you can read that information from, but for now, yeah, we'll know. Okay, so what you need to remember here is that the speed change is related to the part of the, so I'm going to write this as A parallel. And that is the part of the acceleration that's parallel to the velocity. Yeah, I'm just going to leave it like this for now, but I'm going to explain it right now, next. And then this, what makes an object turn, is the part of the acceleration that's perpendicular to the velocity.
What is that symbol from A11?
That's two lines that are parallel. That's the sign for parallel. And this is the sign for perpendicular. Okay, so let me give you a set of steps for visualizing the acceleration vector in 2D. Okay, so first, draw the object and its path in the real world. So this isn't like a position versus time graph or anything. This is the path the object actually travels in space. Draw the object and its path in the real world. So like, for example, the object could be traveling a path like this, and let's say we're interested in when the object is right there. Okay, so second, draw the velocity vector of the object and that's always going to be tangent to the path in the direction of motion. Okay, I'm just going to keep copying this. Okay, so at this point, an object, a vector that's tangent to this path in the direction of motion.
I'm sorry, can you move up a little bit?
Yeah.
Thank you.
More?
Yeah, that's it.
Okay, so remember to draw a tangent to a curve. You can draw two nearby points, draw the line through them. In this case, you would get a vector like this. So that's the velocity vector. Okay, next. So for step 3, you're going to draw the part of the acceleration that's parallel to the velocity. So this is the one we're going to call A parallel. And this is the one that works just like the acceleration in 1D. Okay, so if the object is speeding up, then A parallel is in the same direction as the velocity. And if the object is slowing down, then A parallel is the opposite direction of the velocity. Okay, so, I didn't say, let's say that this is, say it's slowing down. Okay, so now we get down here. If it's slowing down, A parallel is opposite the velocity. So A parallel is this direction. Okay. And now step 4, now we're going to draw the part of the acceleration that's perpendicular to the velocity. Yeah. So this is going to be our A perpendicular. Explain it. Yeah, sure. Well, I mean, I think you definitely just want to go step by step. The velocity always has to be tangent to that path and in the direction of motion. So that's stuff, we've done that in a couple of lab activities so far. And once you know the direction of velocity, you know that there's this part of the acceleration, A parallel, you just have to decide is, based on whether it's speeding up or slowing down, is this exactly in the same direction as V, or is it exactly opposite V? Since this object was slowing down, I knew that A parallel is exactly in the opposite direction of V. Okay?
Okay.
So now the part of the acceleration perpendicular to the velocity. Well, let me move this down. Okay. So now think of fitting, fit a circle to the curve. A perpendicular points in the direction of that circle's center, the center of that circle. Okay, so look at this curve, and at the point that we're looking at here, if you fit a circle to this curve, would it go over on this side, or would it go on this side? It would be on the top. You see that? The curvature of the circle has to fit the curvature of the of the curve of the path. And so in this case, a perpendicular is going to be perpendicular to these two, 90 degrees from these two in this direction. So there's our a perpendicular. Okay, so that's our step 4. And now the last step is 5, and that is the total acceleration is just the sum of those two parts. Well, we know the directions of these two parts of the acceleration, but we don't know the magnitude. That means that adding these is just a vector somewhere in the range between those two directions. Okay, so the total acceleration is somewhere in this range. Okay. So like an example of like a possible acceleration would be like a vector like this, you know, but it could be any of those in that range.
Where does gravity fit into it?
Okay, yeah, that's a good question. Okay, so we have kind of, in free fall problems and stuff, we've thought of gravity as an acceleration. But that's just because the only force on objects in free fall is gravity, so we happen to know how things are going to accelerate. Really, gravity is not an acceleration, it's a force, okay? And remember that acceleration is just telling you in what way the velocity is changing, okay? So, like, in a problem like this, I haven't told you anything about what's making this object follow this path. There's forces, it could be motors or it could be, you know, some other kind of constraint. But if I tell you that the object is following this path and it's speeding up or slowing down, that's all you need to know. Gravity isn't something you have to think about.
So we would never have to combine like, you know, negative 9.81 with the perpendicular.
Yeah, that's right. I mean, we'll see how to do that when we start doing kinetics and start talking about forces. But for now, no, like, yeah, this is something separate.
Cool, okay, thank you.
Yep.
Can you go back to number 5?
Yeah. Okay, so let me do 2 quick examples here. So first, let's think about an object in projectile motion. So this object would follow a parabolic path like this. And let's think about it, and let's say it's going from left to right. Let's think about it once on the way up and once on the way down. Okay. Okay, on the way up, at this point here, a tangent vector in the direction of motion is like this. Now, when a projectile is on the way up, is it speeding up or slowing down? Slowing down, that's right. And so that means that a parallel is opposite the velocity. So a parallel is something like that. Bless you.
Thank you.
And now, based on the way this is curving, if you fit a circle to this curve, would it be pointing like sort of down and to the right or up and to the left?
Down to the right.
Yep, down and to the right. So A perpendicular is 90 degrees from this, like that. Now the acceleration is somewhere in between those two directions. So somewhere in here. And now here's the thing. This is projectile motion that we know a lot about. What direction does the acceleration point in projectile motion? Straight down, remember? Always straight down. And so if this works, a straight down vector needs to fall in that range that we figured out by thinking about it another way. And you can see that it does. So they sort of agree in that way. Okay. So now let's do it for this thing on the way down. So a tangent in the direction of motion looks like this. A projectile on the way down, is it speeding up or slowing down? Speeding up this time. So this time it's going to be in the same direction as the velocity. If you fit a circle to this curve, would its center be somewhere down and to the left or up and to the right?
Down to the left.
Yep, and so A perpendicular is 90 degrees from this in this direction. So the total acceleration has to be somewhere between these two directions. And again, now you can think, okay, projectile motion, I know a lot about that. I know the acceleration is always straight down. So a vector pointing straight down needs to fall in this range. And does it here?
Yeah.
Yeah, that's right. Okay, now what if an object either is staying the same speed or it's not turning? That's what we haven't thought about that yet. In other words, what if you only have either a parallel or a perpendicular? Well, let's do one where an object is turning but the speed is staying constant. Okay, so let's say that the path is this. And let's say that this is where we're interested in it. The velocity vector is tangent to the path in the direction of motion, so this way. Since it's not changing speed, there's no A parallel. Remember, A parallel is just based on whether it's speeding up or slowing down. Okay, so there's no A parallel. We just leave that off. Okay. Now A perpendicular. If you fit a circle to this curve, would A perpendicular go down and to the left or up and to the right?
Down and to the left.
Yep. And so A perpendicular is straight this way. It has to be 90 degrees from this one. Yep.
Sorry, just out of curiosity, but is there a reason that you're saying down and to the left or up and to the right?
No, it's just the way I've drawn it.
Okay.
Yeah.
okay,
I
so
mean,
it
I'm just
doesn't
trying to
really
describe
matter.
that.
Okay.
Right. Okay, so now we know there's no A parallel. We know there is an A perpendicular. The total acceleration is just the sum of these two parts. And this one is 0, which just means the total acceleration is equal to this one. So if one of these is 0, then the total acceleration direction is fully known. It's just equal to the one that's non-zero. Anybody have any questions about that? Okay, that's it for today. So remember, we have a quiz on Wednesday.